Hello world, microcats! Today we will consider the possibility of constructing a circular sonar using a special platform and an ultrasonic sensor. This is the first part, so there will be only rotation mechanics here. In the second part, measurements of the distance to objects will be made. We turn on the power supply for the microcontroller and the platform. The electric motor begins to rotate and set the gearbox shaft in motion. A movable part with modulus is fixed on this shaft. The wire connection is done on the breadboard. It also has a transistor driver for the motor. The microcontroller shows rotation information on the display and gives short signals to a green LED and buzzer. Data transfer from the stationary to the movable part is carried out using a rotating contact device. When the centers of a light and photodiode coincide, a sound signal occurs. The sonar consists of a metal base. A motor with a gearbox is mounted on it. A rotating contact device is fixed on its shaft, and on top is a movable part with an infrared LED and an ultrasonic sensor. A breadboard is attached to the base. A photodiode module is attached to it and a motor driver is installed. On the moving part to the contacts of the ultrasonic sensor, wires are soldered for constant power supply of the infrared LED. When the power is turned on, we see a purple light. It is visible only on the phone camera. Let's take a closer look at a mechanical sonar device. The bottom plate has corners and bases for support. The rotating device is attached to it through 6 corners and 3 racks. The inner movable part is fixed to the shaft with silver bushings. The ultrasound sensor and infrared LED board are rigidly attached to the shaft. Close movement. The system for calculating the speed of rotation is built on light and photodiodes. Movable LED emitting continuously. A fixed photodiode gives out the signals only at the moment when their centers coincide. At this moment, the controller sends a signal to an external green LED and a buzzer. The most important thing is that they have one single point of meeting of their geometric centers. With the help of a timer, the controller catches the leading edge, thereby making a new revolution. The duration of a revolution is calculated precisely by the leading edge of the pulse, which occurs at the moment the LED passes over the photodiode. And so the centers coincided, the signal to the external buzzer and the LED came. Now the display is used only for giving information about the rotation of the moving part of the sonar. Frequency, RPM, period in seconds and microseconds are calculated. Due to the low rotational speed, and the data update rate is also low one time in 10 seconds. This value can be reduced only in the loss of accuracy if you do not average the data but give out the values measured at one revolution as true. A small overview. We start from the top with the moving part with sensors. Below is a gearbox on a platform and a breadboard with a photodiode module. The communication between the sonar and the controller is by wire. We see the blinking of the LED which fixes the onset of a new turnover. The buzzer sounds in time. The turnover data is updated on the screen. Consider the electrical circuit. An ultrasonic sensor and an infrared LED are located on the moving part. The sensor will be discussed in the next section. The LED shines constantly and describes a circle of radiation to a fixed part downward. This radiation is received by the photodiode module. It is installed on the off points of a circle. When their centers fall in, a buzzer and a green LED sound for a short time, 50 milliseconds. Sonar movement is impossible without an electrical motor. Here it is used with a built-in gearbox. A special transistor driver is used for the motor, a current amplifier. The driver is controlled by an Stm32 microcontroller. It also receives a signal from the photodiode module and issues a light and sound alarm. Additional information through the interface SPA1 shows on the screen. Here we used a Stm32 screen, 160 by 128 pixels. Let's consider the software part. We declare global variables and include the necessary header files. In the main function we configure the peripherals. Setting up an object to work with the display. Set the slow speed of a sonar rotation. In an infinite loop, we call the function of measuring the engine speed. Its measurement time is 10 seconds. It takes such a long time to accumulate several measurements and calculate their average. The time of one revolution is long enough. Based on the received frequency, we calculate the additional values of the variables. We display all the data on the screen. In the measurement function, we first reset the variables used. We start time 4 and wait for the required time. It must be longer than the time of a full revolution. After that we check the number of edges. It is equal to the number of measurements and calculate the arithmetic mean. Stop timer 4. The interrupt handler for timer 4 has two input events. The first is an update event. It happens every millisecond. We just increase the counter. In the capture event, turn on timer 2, this will give a light and sound signal. We calculate the difference between the current and the previous measurement in microseconds, taking into account the overflow. We store the difference into an array of measurements and the current captured value into a special variable. After processing the interrupt, we have a data array, each element of which is the value of one revolution of a sonar shaft in microseconds. Setting up pins. The PWM signal for the motor is port A, pin 8, alternative push-pull mode. The signal from the photodiode module is port B, pin 7, input floating mode. The PWM signal for the buzzer is port A, pin 0, alternative push-pull mode. Setting up timers. Timer 4 is used to capture the signal from the photodiode module as the sonar motor shaft is rotated. The duration of a single tick is 1 microsecond. The duration of a period is 1 millisecond. Channel 2 catches the leading edge. Digital filtering is at its maximum. The timer is switched on and off is a special measurement function. Timer 1 is required to generate a PWM signal to the motor. Its temporary settings are similar. The timer has a PWM output to the main channel number 1. The polarity is positive. The timer runs immediately, but the PWM parameter is configured in the special function set motor velocity. Timer 2 is required to generate a PWM signal to the buzzer. Its period is 100 milliseconds and the operating mode is one shot. Its channel number 1 is also configured as an output pin. The PWM pulse has a duty cycle of 2. That is, in fact, the light sound signal has a duration of 50 milliseconds. The output is active in idle mode. While the active level is low, such settings allow you to start a timer that will give a positive pulse and turn off while resetting its output. For timer 4 interrupts and their events must be configured. That's all, see you in the next video. Subscribe microcat.